Hello, everyone. My name is Brian Cunningham, and I'm with ELPRO Technologies. Today, we're going to talk about how to do a site survey to test a wireless link. Okay, now, the range of a radio system is influenced by the frequency of the radio system, the transmit power, and its receive sensitivity specification. Now, of course, the range is also influenced by external factors like obstructions in the path, how high each antenna is mounted above ground. But as far as just the hardware goes, just the radio selection, it's going to be influenced by the frequency, the transmit power, and the receive levels. Now, we have a bunch of different radios that we manufacture. They operate on all kinds of different frequencies, so they are going to have different frequencies, keeping in mind the lower the frequency, the greater the distance, and the greater the object penetration ability. We have radios with different transmit powers. They vary anywhere from a low of about 200 milliwatts, going up to 5 watts of transmit power. And of course, as you can imagine, the more transmit power you have, the greater the distance. Then we have the receive sensitivity of all of our different radios. Most of the radios that we manufacture, the receive sensitivity is around negative 110 dBm. However, we do make a number of very high-speed radios. These three products right here, high-speed Ethernet pass-through modems. And for those products, the sensitivity threshold is about negative 90 dBm. Now, those are threshold levels. So what that means is that we want to have a suitable fade margin because we don't want to be operating right on the absolute edge of reception of the equipment because we would experience intermittent operation. So we want to have a fade margin of minimum 10 dB, better than the minimum sensitivity of the radio system. Now, there's some other factors that we'll talk about in a couple of minutes, like background noise. Our signal, of course, has to be stronger than the background noise, otherwise you won't be able to hear our radio transmitting out of the crowd or our radio speaking among the crowd. To make an analogy to people sitting in a coffee shop, if the coffee shop is full and everybody's talking away, then you have to talk a little bit louder for normal communications than you would if that coffee shop were empty and there were no background noise. Okay, so now there's two types of surveys that can be done. We can either have a software model or we can do on-site surveys. And there's some big differences between the two. The software model, what's involved there is you would determine the GPS coordinates of all the locations. Then you would enter them into a Pathloss software program. And the Pathloss software program then downloads the terrain data from the U.S. Geological Survey website. And it also downloads land cover files that show what areas have trees, what areas have buildings, and different types of land cover. Now, they're relatively easy to do because you don't have to drive on site. You can all do it from your office. And what it does is it's designed to calculate how high each antenna needs to be mounted above ground to get suitable reception. And now, because it is a software product, you do have to have some skills. Somebody has to know how to enter the data correctly. Somebody has to have some experience with the program. And in other words, have done a couple of models and then have gone on site and done an actual hardware test and compared the two to make sure that they're accurate. And you have to have a little bit of knowledge of RF. So it's not the simplest thing in the world, but if you have had some experience with radio systems, you should be able to figure out how to get a Pathloss software program up and running. Now, companies usually charge for these. There's a bunch of different programs out there. They can cost anywhere. There's a free program out there. There's also other ones that can cost several $1,000s. So there is some cost associated with using software. On the other hand, if you have the actual radios on hand and you have some antennas and you have some means of elevating the antennas above ground, then I would always recommend an on-site survey. The on-site radio surveys will always be more accurate than a software model. The on-site surveys will also account for interference from other systems. So if the radios don't link up because you have too much background noise from another radio system nearby, that will show up in the on-site testing. But of course, the software model does not have the ability to determine interference from other radio systems. So the on-site surveys, obviously a little bit more expensive, requires you to actually boots on the ground on the sites. You have to have hardware on hand and this sort of thing. So there are some differences between the two. A lot of times we'll actually do both types of surveys. We'll do a Pathloss software model to see if the radio link is even feasible, whether we're in the right ballpark or not. And then at the later point, we will go out and actually test these and make sure that the software model is accurate and reflects real world conditions. So here's an example of one Pathloss study that I did quite recently. It involved doing a backhaul to a plant location from a landfill site. And they're monitoring a variety of different parameters at the landfill. Usually it's methane gas related. And they're sending all this data back to a central point where they consolidated all the data. And then we found, because of this distance, we had to use a 450 megahertz 5-watt radio to do the backhaul all the way back to this the plant location. So what we did is we went through all the calculations and figured out approximately how high the antennas need to be on each end here. This is one of the profiles here from that study we just saw on the previous page, and here's all the information that it will show you. This is the land cover file that is downloaded, and this shows there's a number of large buildings. These are commercial buildings here. These are trees, and we can see there are different types of trees. So the land cover file shows you the different types of foliage that's in the path and the approximate height as well. So very valuable, incredibly useful information is available for free. These data files can be downloaded free of charge. The ovals that you see here, they represent something called the Fresnel zone. And we have the first, second, and third Fresnel zones. And in a nutshell, 60% of this three-dimensional stretched football has to be free of obstructions for suitable propagation. And this software program calculates all this information for you. The other thing you can see is the terrain file that we have downloaded. So you can see the terrain goes up and down and varies and all that sort of stuff. And this all influences the Fresnel zone. And again, the software calculates the whole thing, so you don't have to worry about these unbelievably complex calculations that go into all of this into all of this information. So there's a bunch of information that we can determine here. I'll just show you the highlights here. First of all, the distance for this particular one is 7.23 kilometers, so it is a fairly long distance radio length. The received signal strength is predicted to be negative 85 dBm. And given our threshold of reception for this radio, approximately about 100, negative 100 dBm, so we have about a 15 dB fade margin. Then we have the transmit power. We have this radio set for 5 watts. Then we have the antenna gain. So we specify that they must use a 12 dBi Yagi antenna. And you can see that specified on both ends. Then we have the antenna heights of each end. And in this case, this antenna must be mounted 17.5 meters above ground. And on the opposite end, this antenna must be mounted 8 meters above ground for suitable reception. And you can see that at 8 meters, it looks like it's just clearing that foliage right in front of it. And on this end right here at 17.5 meters, we're still shooting through a whole bunch of buildings and a lot of terrain coverage. There is no line of sight. But at 450 megahertz, we can get away with that. The lower the frequencies, the much better object penetration ability. So what we can do is we can increase and decrease the antenna height. And in doing so, it will recalculate the received signal strength. And we can increase or decrease it until we get our optimal signal strength here. If we wanted to, we could also change the frequency. We could test it at 900 megahertz or other frequencies as well. So these software programs are very, very capable, very interesting. They provide you with a lot of information, and they generally provide you with a go or no go. Will it work? Will it not? What sort of heights are we dealing with? If the customer came back and said, we can't mount an antenna this high, it's too expensive, then we can say, well, hey, is there maybe a repeater site halfway in between, or could we get around these buildings so that we're no longer transmitting through them? So it provides feasibility studies, and then we can look at the realities of, can we mount an antenna this high above ground at the two locations here? So very interesting information that these Pathloss software programs can provide. Okay, now one of the first things you'll have to do when you're talking to a customer about a installation, how far apart are the locations? And I'm going to tell you a little joke here is, and this is human nature. When I ask customers on the phone how far apart sites are, oftentimes you'll get answers like, "Oh, it's not that far, really. You know, it's not too far." And of course, you know, I need an answer in, you know, feet or miles or kilometers or something like that to put it in perspective. So I often joke, could you hit it with a baseball, or would you need a golf club? And I had the customer immediately say, oh yeah, it's a 9-iron shot for me. Obviously I was talking to a fellow in golf, and I said, oh great, well that means 90 yards. That tells us pretty much the distance bang on. So if you can put it in terms of customer respond, you know, can relate to, it'll make for a much more interesting conversation, of course, as well. So, but what we really ask for is, can you provide the coordinates in Google Earth? And then we can, if they can put push pins into the locations on Google Earth, as you can see in this image, they can save that information as a Google Earth KML or KMZ file, and then they can email that information to you, and I can open it up and I can have exactly, I can look at exactly what those sites are going to look like. Then we can import that information into my Pathloss software program, and we can figure out how high each antenna needs to be done and what the best layout is, and which sites would make the ideal repeaters and all that sort of stuff. Now, these Pathloss models, generally we recommend them for anything over about a half a mile, because less than half a mile and the terrain data, the GPS data that the U.S. Geological Service provides is somewhat coarse. So they'll have mapped an entire area, and they'll usually every 10 meters or so, they'll have an elevation data point. But if we're looking at trying to do a Pathloss study for a distance of you know, a quarter mile, well, there's probably only 3 or 4 data points that we're going to be going on, so it's not terribly accurate there. Now, then in terms of distances, compared to the data sheet distances that we print or all of our competitors print, and of course we all print the absolute maximum range, because that's what customers want to know. You know, if you're buying a Ferrari and you can't decide, should I buy a Ferrari or a Lamborghini? Well, one of the things you're going to look at is, what is the maximum speed? And of course, that's the absolute maximum. We and all of our competitors do the same when it comes to distances for our radios. So I generally suggest aim for about half or 50% of the maximum range for easy and workable links. And I say this because antennas need to be mounted higher and higher above ground as the distance gets greater and greater. And that's because of curvature of the earth, the Fresnel zone, and obstructions and things like that. So if we're going to try to get the maximum range out of all of our radios, we're going to have some pretty tall towers. And oftentimes, if that means the antenna's got to be mounted, 120 feet above ground, well, that may not be practical. The customer might say, that's simply too expensive for me to build a tower that tall for the antenna. So that's what we say, aim for 50% of the maximum ranges for easy workable links here. Oh, here we go. This is just showing another Pathloss study that I did a while back as well. And you can see the terrain cover that we have in between. We can see our Fresnel zone coverages as well, the received signal strength, and you can see where we were shooting to here. Okay, so yeah, those Pathloss studies are very, very useful for providing a preliminary view of whether it will work or not. Now, here are some typical ranges for a 900 megahertz 1 watt frequency hopping spread spectrum radio. Now, we also make some 900 megahertz direct sequence radios that have less transmit power. They would have slightly different ranges. So this is for products like our 915U2, the 905U-1234 radios, the 905UK, et cetera, et cetera. So here we go, 600 feet, densely obstructed, typical industrial plant with piping and bulkheads and machinery around. No line of sight. LOS is short for line of sight. We would just use our CFD 890L, which is a 16-inch tall Omni antenna with 15 feet of coax here. And we can go on and on. Generally, when we reach about 10,000 feet and we don't have line of sight, that's the cutoff point. The radios won't link up beyond about 2 miles unless you have line of sight for this type of radio and its frequency. And here we go. So anyway, we have these charts for all of our types of radios. So the 450 megahertz, the 2.4, the 5 gigahertz. I've got a chart that gives you typical distances and what antennas we recommend there. Now, here is the line of sight requirements for all the various models of radios that we make. For the 915U2 and the 905 series, it's 2 miles. For the 945U-E, roughly 500 yards. Anything beyond that, we need to be, one antenna needs to be able to see the other. The 215U2 are 2.4 gigahertz radio, roughly 50 yards. The 415U-2, 450 megahertz, 5 watts, 4 to 5 miles. And then we have our high-speed Ethernet devices, the 2.4 and the 5 gigahertz, 150 and the 25 yards there. So beyond that, you generally need to be able to see the other antenna, so they will have to be mounted fairly high up. Now, I want to take a minute to show this photograph here. What this is this is a trailer-mounted flagpole. It's a telescoping flagpole. And what our distributor did was they just mounted the antenna directly to the top of the flagpole mount. They telescope it out. It connects to a standard 2-inch hitch on the back of a pickup, and it has a little base, so the antenna is resting on the ground here. So this is a very useful accessory, and I think the company is Telescoping Flagpole, or if you Google that, you'd be able to find a couple of companies that make similar devices, and they all mount to the hitch of a vehicle. Okay, so some of the other questions we're going to have to ask is what is in between, or what is blocking line of sight if we're going for a shorter distance here? Generally, the more dense the obstruction, the greater the attenuation of the radio signal it will be. Now, keep in mind, radio waves cannot pass through metals. So, for example, if we have an antenna inside of a corrugated steel building, we have to mount the antenna outside of that building. Now, there will be exceptions if the building has windows. If there is a couple of windows in the direction that we need to shoot the signals, then it might work, but we probably have to test it with a demo kit. And I'm going to talk about our demo kit in a couple of minutes as well. Now, these radios also cannot shoot through land, through earth, so we can't shoot through a mountain. Now, the 450 megahertz radios, we can shoot through a little bit of terrain, but as a rule of thumb, you're just not going to get that far if you're trying to shoot through a hill or through a mountain. But they could shoot through the 450 megahertz radios can shoot through a berm or relatively small land, earth-based obstructions like rock and dirt is what I'm talking about. Now, one important thing is to avoid obstructions immediately in front of either antenna. So in this case, we're okay because let's say that tree there is about 100 feet away from that antenna. We should be good. But if that tree were immediately in front of that antenna, what happens is the radio waves undergo a scattering. So they hit all the leaves and the branches, and they get scattered all over the place. And one of the ways to think about radio waves is they are on the same type of spectrum as light rays. So if you had for example, if it was the middle of the night and you took a flashlight and you aimed the flashlight at the opposite location, if there were just a couple of trees in between the blocking line of sight, you would probably still be able to get a fair bit of light behind those trees. But if you had a big tree right in front of that flashlight, or analogy to our antenna, then it's going to scatter a lot more light rays away from the direction that we need to see it in. So again, the best way to think about the propagation of radio waves is just like a light ray, because radio waves are on the same electromagnetic spectrum as light rays. Radio waves are just at a lower frequency than light rays. So the propagation is going to be very similar. Okay, then once we've got a rough idea of what we're doing, we've got the GPS coordinates, we know the distances, we know roughly what sort of obstructions there are, then we have to visit each site to assess the following there. Is there a structure we can mount our antenna onto, like a pole, the side of the building, something like that, or is the customer going to have to pour a concrete pad and mount a pole? The customer needs to be prepared to do all this, of course, so this is where we need to figure this out here, so they can calculate their total budget for the project. Then we have to figure how much coaxial cable do we need to allow the radio to be mounted at ground level so that we can easily plug into it and access it and view the LEDs on board, to the antenna, which has to be mounted up high. Do we need 50 feet of cable, 100 feet of cable? What is the horizontal and vertical runs of coax needed? Is there power at the site? We'll need either solar, mains power, 24 volts, whatever. These radios need power, so we got to think about that as well. Are there any other antennas within a 100-foot radius of where we want to mount our antenna? If so, then we need to make sure that we space our antenna a suitable distance away from the other antennas. Now, we have a chart that shows antenna separation versus frequency. And I'm happy to share that chart with you. So if you go onto the roof of a building and you discover that there are already a few other antennas on the roof of the building, all we have to do is just find out what frequency those radios are operating at, and then we can figure out how far away we need to mount our antenna to make sure that we don't cause interference to their system and they don't cause interference to our system. Another thing to look at on site is what obstructions in the immediate proximity, like directly in front of the antenna, are there, as we just discussed in the previous slide. And what does the view look like towards the destination? And this just gives us, this is a boots on the ground thing to give you a much better impression as to what obstructions are there in the path. Is it buildings or houses? Is it just trees? And how dense, how many buildings or how many houses or how many trees are in the path? And then, of course, to be able to pick the correct model of radio, we need to figure out how many I/O points or what type, like how many 4 to 20 signals and how many discretes, or is it Ethernet, or what's the interface at this location. Okay, so ELPRO has a demo kit, a site survey kit. We have asked all of our distributors to purchase one of these demo kits so that they can go out and be able to prove these radio links to customers. And this is what the demo kit looks like. We've got a bunch more pictures that'll show you the whole thing here, and I'll talk about that quite a bit. But one of the things to be aware of is charge the batteries the day before. Make sure you're good to go. Power up and test the demo kit in the office before you leave. You don't want to be on site and find out it's not working or something doesn't function quite properly. And bring back up high gain antennas and cables. So, for example, if your small antennas don't do the trick, we want to have a high gain antenna as a backup so that we can swap out the small antenna with a high gain antenna, and the higher the gain, the greater the range, and see if that will provide suitable reception. Then figure out the antenna orientation beforehand. On the antennas need to be pointed vertically. They should be no more than about 5 degrees tilted to either side. And Yagi antennas need to be aimed in a specific direction, and their crossbars or their elements need to be vertical. Generally, it's best if you have 2 people when you're doing these site surveys so that one person can keep an eye on one end of the radio kit, make sure the antennas haven't fallen over, because these are always going to be temporary installations and that sort of thing. And also with our kit, you can send some signals back and forth, and you can switch this switch here, and you can do a communications check on the opposite radio. And it's handy if you can have the opposite fellow change some I/O and have a look at it on your location. It also does a lot to convince the end customer that these radios do indeed work, and everything will work out just fine. Plan the sites and the driving time. If you have to do a survey of 30 sites, you got to figure out how can we do this most efficiently so we don't waste a lot of time driving around the neighborhood. Then we need to think about repeater sites. If some of the sites don't link up, what site would act as an ideal repeater? Usually it's a location that is at a high point that has a clear view of the more distant sites that cannot shoot direct to the master radio. Okay, so when you're on site with our demo kit, we start with the smallest or the lowest gain antennas. And then we start with the antennas relatively close to ground, or whatever is a convenient mounting height. I mean, that might be 10 or 15 feet above ground, because generally that can be, a pole can be mounted at that height very inexpensively. Then if reception is not sufficient, we gradually raise the antennas. And we have to make sure that we, again, keep clear of obstructions immediately in front of the antenna. And again, if we look at this diagram right here, and we envision this is a nighttime, let's say we're at midnight, and there's no light, and we have a flashlight at this end here, and we want to see how much light we can get at this end here. Well, if there's a big tree right in front of that antenna, it's going to be a much bigger obstruction than if that same tree were mounted right here. So you can almost imagine, you know, if you take a flashlight and you're shooting it out in this direction here, you're going to get a lot more light at the top of that tower if the tree is mounted right here, as opposed to directly in front of that antenna or that flashlight in our analogy. And again, this is showing the Fresnel zone that has to be 60% clear of obstructions. It's a 3-dimensional stretch football that has to be 60% clear of obstructions for suitable propagation. Okay. So if the signal is not strong enough, then connect a higher gain antenna. Then with the higher gain antennas connected, raise the antenna height. And then have the remote site also do the same things to practical maximum antenna heights. Okay, then we need to write everything down. We need to have the documentation. So we need to write down the name of the site and the received signal strength. Then we have to write down how much coaxial cable and what type of cable did we have connected there. Then we have to write down how high did we have the antenna mounted for our test. Then where on the site did we have that antenna mounted? Like, for example, did we have it mounted on the north wing of the building, or was it mounted on the east side of the building, et cetera? Like, where, the specifics of that particular site. Then we have to indicate the direction that the antenna needs to be aimed. Your compass, you can just use your iPhone. They have a compass app there, and you can figure out where the antenna is being aimed. So you write down that direction so the installer knows what direction to angle that antenna to. Then we should note background noise level, or are there other sources of interference nearby? And I'm going to show you a spectrum analyzer screen that I have in a couple of minutes here. Then we have to mark down the actual radio settings and the hardware used. For example, are we testing with a 915U2 demo kit, but we plan to use the 945U-E in the final installation? Because those radios are both 900 megahertz, you can use a 915U2 to test a 945U-E radio link. We just need to know that the transmit power is going to be less on the 945 and the receive sensitivity is lower. So we simply have to have a much stronger RSSI. For example, with the 915U2, we can get away with an RSSI of -90, and that gives us a suitable fade margin. But with the 945, that same radio has to have an RSSI of -70 now. So as long as we're using the same frequency during our site survey, we can substitute other radios for the final installation, as long as we know what the difference in the sensitivity of those radios are, and if there is any difference in the transmit power as well. Then we should note the weather or the seasonal conditions on the test date. The major factor that we're looking for is, are trees in full bloom, or are there no leaves on the trees? Ideally, we want to do radio tests in the summertime when the trees are at full bloom and they are most dense and representing the biggest obstruction. Of course, that depends on whether there are trees in the path. If you're shooting across an area that has no trees, obviously we can do site surveys in the wintertime or whatnot as well. Okay, some things to be aware of. One systems integrator I was dealing with had a Pathloss software study done by a third party. This is the program down here. And I replicated the exact same program with my Pathloss software and found that the radios would not link up. So I would be careful of getting into a position where you're guaranteeing reception based on a Pathloss study another company has done. So I would suggest it's fine to supply the hardware and do the installation and the programming of the radios, but certainly we cannot guarantee the results based on the specifications that another customer, a third party has provided. That would be their responsibility. For 900 megahertz radios, be careful of these types of pine trees. And I'm specifically referring to the type of pine trees that have the 3-inch long needles. They resonate at 900 megahertz. Just strictly by coincidence, but if you've got these, I think they're called ponderosa pines, but don't hold me to that. Again, the ones with about the 3 to 4 inch long needles, they represent a much more dense obstruction to 900 megahertz only. So one pine tree is going to be the equivalent of about 5 regular deciduous trees. Another thing to be careful of is 2.4 gigahertz interference coming from Wi-Fi in offices or apartment blocks. If you have to shoot across an apartment block, just know that every single unit in that apartment is going to have their own Wi-Fi hotspot. So they can be very difficult to use 2.4 gigahertz in dense urban environments in particular. And also just be aware, the longer the distance, the more difficult it is because you have to have equipment to be able to climb up and mount the radios up higher. The more expensive it is because the taller the tower, the more it's going to cost. We need higher gain antennas, we need longer runs of coax, etc. And ultimately, it can be less reliable because, as you can imagine, if you're just shooting, say, 1,000 feet, the signal strength, the signal to noise ratio is going to be incredibly strong relative to if we're now shooting 20 miles and we are now much closer to the threshold of reception of that radio. So the shorter the distance, the stronger the signal to noise ratio. The stronger the signal to noise ratio, the more reliable the radio system becomes. And keeping in mind, the vast majority of radios that we do, they need to be operating in our field, the industries that ELPRO deals in, water, wastewater, oil and gas, mining, those are all heavy industries. They need reliability 24 hours a day, 365 days a year. So quite often I will get involved in dealing with outages that occur for a few seconds a month, and this can be a problem for a customer. So at ELPRO, we have become experts in making sure our radio links are extremely reliable. The other thing to be careful of is other antennas or cellular towers. And I'm going to talk about cell towers in just a minute. Other antennas, we just need to find out how many feet or yards they are away from our antenna and what the frequency is. And we have antenna separation charts. So this is why you can see on this diagram here, you can see a bunch of antennas, or they're all mounted a little bit a ways away from each other. And this is because antennas do require separation from one another. Okay, here we go. This is one shot. This is for an electrical utility project that we did a couple of years back. You can see our Omni antenna is right here, and this photograph was taken up on a bucket truck. And you can see that's a cellular tower on the far side of this electrical substation. Now, I wanted to just quickly mention electrical substations do not pose interference to our radios, and this is because they're operating at 60 hertz. So any harmonics that they would produce up at 900 megahertz would be negligible. So we can take our radios, we can have a radio right over here, and we can be shooting right through this electrical substation with no issues there. Of course, in this installation, it was a long distance radio link. We're doing several miles. So we had to have the antennas much higher above ground. So what we try to do is we try to keep our antennas approximately 300 feet away from a cellular tower. And that just keeps us in a safe zone. Now, we actually, I can tell you, we did have one installation where we mounted our antennas on the cellular tower. What we did is we mounted our antennas about 15 feet below the cellular antennas, and that meant they were out of this radiation pattern. So the, if you can imagine, it's a beam of radiation coming out of those. The strongest radiation is going horizontal. So these antennas aren't designed to radiate any information into the ground. So we could mount our antennas below these cellular antennas on the same tower. Okay. Now, if we had to shoot from this antenna directly to a remote site that was in line with this cellular tower, that's going to be a problem. That won't work very well, especially if we have a Yagi antenna that we're aiming at this cellular tower. So that's going to be a problem. That will not work. So what we would have to do is we would have to reorient our antenna. So for the substation, what we would probably do is we would remount the antenna over here so that now we're no longer shooting directly at that cellular tower, trying to shoot through it, literally. Now, if you go to the top of a hill or the top of a water tower and you discover, wow, there's already a bunch of antennas or cellular towers that are already up here, there are some other tricks that we can do, like we can shield our antenna. Or we can, basically shielding is the same as mounting it behind a building so that it does not have line of sight to the tower. So if we could orient the antenna so that it did have line of sight, the remote site that we're dealing with, but did not have line of sight to the tower, then we basically made sure that we're not going to have a powerful source of interference coming off the cellular tower going straight into our radio. As well, there are some other tricks that we can do. We can use a filter in line with the coaxial cable and the antenna to block frequencies outside of our frequency band. So this is something that's not done very often. We generally try to engineer the system so that we don't have to worry about that. Once in a blue moon, you might have to go buy a filter and install it in series with the antenna. Okay, so a couple of things to be careful about. Never test in bad weather. Lightning storms and radio surveys do not go well together. While you're up in the bucket truck, be sure to enjoy the view, because it's a rare treat to be able to survey the land and really enjoy the view. Double check your fall protection. Make sure you've got your harness on and it's properly secured. These bucket trucks can be quite dangerous, and they can move rather abruptly. Plan the orientation of your laptop and other equipment in the bucket truck so nothing goes overboard. Watch the proximity to power lines. This is very important, folks. Nobody wants to have an accident on the job. If you have a spectrum analyzer, connect it to the antenna at the same height as the final installation so that you can see what sort of interference your antenna can hear at the height that it's mounted. And if we, for example, if we have a spectrum analyzer and we're able to see interference is at, for example, a level of -90, the RSSI has to be 10 dB stronger than that background noise. So the RSSI would have to be -80 at that site to be functional. And as long as it is, we are good to go. This is a spectrum analyzer that I've used in the past. This is the type of display that you'll get across it. You'll see the frequency 902 is on the left-hand column, 928 is on the right-hand column. And what this is showing the level of interference at all of these different frequencies right across the spectrum. So in this case, we've got three plots being shown. We're showing the average, the peaks, and then the density of interference. In other words, the duty cycle of that interference. So you can see we've got a lot of peaks here, and on the left-hand side, we have the amplitude. So we start off at -100, -90, -80 dBm, and really what we're looking for is where the red stuff comes in. And you can see that there's a fairly consistent blast of interference right at this particular frequency, and that the duty cycle and the overall interference levels tend to drop off at the higher end of the spectrum for this particular site. Now, one of the things I do want to share with you is that I don't quite know why this is, but at almost all sites that I've surveyed in my career, and I've been doing this for about 20 years now, there is almost always higher interference in the lower half of the 900 megahertz band. Now, it doesn't help that ELPRO's default frequencies are also set to the lower half of the 900 megahertz band. So generally, and this may be the case with many other manufacturers too, and that simply might be why this occurs. But as a general rule of thumb, and this is just strictly my experience speaking here, there seems to be less interference in the upper half of the 900 megahertz band. Now, I could be wrong about this. It could be coincidence about the sites I've looked at, but this is just my experience over the years. Now, I wouldn't get too hung up about looking at about buying one of these spectrum analyzers and having a look at it and measuring the interference. That might be good if you suspect there's a lot of interference in the area, but for the most part, all we have to do is just separate our antenna from the other antennas in the area, and we should be good to go. So I wouldn't get too hung up on all this, but this is what the professionals will use. Okay, so then once you have finished your survey, the next thing to do is present it all to the customer. And here we go. This is the one survey I did several years ago. We have the location, the lat and long. This was for an electrical utility, so we gave them their pole number. We measured the noise floor at all of these locations. We monitored where the best spectrum was going to be. We told the customer how high each antenna had to be mounted above ground to get suitable reception. We told them the model of the cable they need to use, the model of the antenna we recommended, and then we showed the estimate of the received signal strength and what location each remote site was shooting back to. So this is a lot of information. You don't really have to provide all of this information, but the key things we would want to know would be, what is the antenna height? What is the noise floor? And of course, what hardware do we recommend to all of these remote sites? Okay, now I just want to spend a minute talking about our demo kit. This is what it looks like here. This is how we can pack the whole thing into a Pelican case with some foam around it here. The Pelican case, a great little box here. You can check it into airline luggage as well. It's got wheels on the bottom, retractable handle, so it's just like airport luggage. And what we do, as soon as we unpack it, we mount the radios on the DIN rail strip that you can see at the back here. We plug in this terminal block, so the whole terminal block just pops out. So you don't have to rewire anything. I would never recommend disconnecting any of these wires, because otherwise you'll have to figure out how it is wired. And there's a power switch in the back. We just turn on the power, and then we're good to go. Now this demo kit, it's designed to send a 4 to 20 milliamp signal from one radio to the other. Then we have a graphical display on this end here, our HMI. And what I'd recommend is this should be the portable end. So this should stay at the master site or your base location. And I would bring this one out to all of the remote sites because it has a better display. It shows you the RSSI in a digital format that's much easier to read. Okay. And we've got a few demo things. We can simulate a pump running. We can turn the pump on and off from this end here. We can introduce a fault to the pump. We can change the 4 to 20 milliamp display here with this dial right here. And we can also change, it's a dual purpose display. We can show either milliamps or the RSSI by flicking this switch to one position or the other. So it has an extra couple of features that are generally designed for trade shows, if you want to do a tabletop trade show. Now, some of you might be wondering, what is this thing right here? That is a 20 decibel attenuator in series with the antenna. And the purpose of that is these radios are side by side. Normally they would saturate and the signal would become too strong and it may become intermittent. So by sticking our attenuators on, we're able to have these radios operating side by side and the received signal strength in our desired range. Here we go. This just shows you a couple of the displays on the HMI page. The most important one that we're going to want to look at is we're going to want to look at the radio site survey. The digital I/O, the analog I/O, this just tells you what the 4 to 20 value is on the opposite end. Tells you what the status of all your digital I/O points there. But at the end of the day, we want to be looking at the radio site survey because that one shows you what the RSSI values are. So this shows you what the RSSI is. This shows you the background noise that the radio is measuring. And this calculates your fade margin. The fade margin is either the difference between the background noise or the difference between the radio sensitivity. And the radio sensitivity is just a value that you enter into the HMI. and it's based on the data sheet. Now, if the background noise were stronger than the radio sensitivity, this is basically nothing. This is saying this radio did not pick up any background noise at all. But if the background noise were negative 95, it would calculate the difference between these two, and your fade margin would then be 30 dB, the difference between negative 95 and negative 65. So what we want to do is we want to take a picture with your phone, or we want to write down what this RSSI value is at each remote site. Then we have the communications check page. Really what this is doing is this is now showing you the RSSI on both ends. Normally the RSSI of the remote end and the master site, they will be the same or within the accuracy spec of the circuitry measuring the signal strength. The accuracy spec is plus or minus 3 dB, so there could be a maximum of 6 dB difference between these two numbers, but generally the RSSI will be the same whether you measure it from the master radio or the remote radio. Okay. So typical RSSI values that we're looking for, we want negative 90 as a minimum. Negative 85 is generally preferred. Negative 80 or stronger is rock solid. And negative 50 is the strongest reading that this demo kit will show. Now, this is for a 900 megahertz, 1 watt frequency hopping spread spectrum radio. For direct sequence radios, the numbers will be different. Okay, the demo kit also has a couple of other screens here. You know, you can do some trends. You can plot. This just shows it's a 2-minute history, and it's just a scrolling screen that shows you the past 2 minutes. And you can plot, you know, RSSI, radio length, background noise, etc. on all on the same screen there. We also have a screen labeled supplies. Shows you what the current power supply is. We want to just look at the battery supply. The battery is it's a 12-volt battery. When it's got 13.75 indicated, it means that the charger is plugged in and the charging circuitry is charging up the battery. But if the battery voltage gets down around 11 volts, you're not going to have much time left. It'll just be a matter of minutes at that voltage level before the kit dies and the battery needs to be recharged. Okay, very last thing here, the demo kit HMI screen here. This is only for the 415U2. One thing I should have mentioned is that the demo kit is suitable for testing radio links at either 450 megahertz using the 415U2 radio, or at 900 megahertz using the 915U2 radio system. So there's one extra screen for the 415U2, and it just shows you your channel utilization. Like, how busy is this frequency right now? Is somebody else using my my frequency channel or not? And it breaks it down to how often did the transmits fail, or how often did the transmits have to do retries because somebody else was transmitting, or it did not get an acknowledgement from the opposite radio. So that's pretty much it for today. So just in quick summary, to test a radio link, there's 2 methods. You can have a Pathloss software survey, and the second method is on-site with the hardware. When you're on-site, make sure you document what antennas you use, what the RSSI was at each remote site, and where the antennas need to be mounted. And with that, I wish you good luck in your site surveys, and thank you for listening today.